Hello, and welcome to another openFrameworks audio programming tutorial. Today we will be talking about parameter smoothing. Let's continue again from our previous project. If you are not following along, grab a copy from the description of the previous tutorial. First, let's discuss what is meant by smoothing. Often, a point of confusion is made when talking about audio filters, like an EQ, and other forms of DSP. There is nothing special about a stream of audio. It is simply a list of numbers like any other digital signal. Therefore, a smoothing filter could be considered, and is actually identical to, a low-pass filter. High-frequency content is attenuated. There are two basic approaches. One is to use linear interpolation and ramp to the number you are going to over a determined amount of time linearly. Linear interpolation will be covered in a later tutorial. Another approach is to use a one-pole infinite impulse response low-pass filter. Again, we will not actually be filtering audio directly, but parameter data used to create this audio. I have made a max patch to demonstrate the differences between these two methods. Alright, so on the top you can see unadulterated signal, the signal as it is without any filtering. The middle method is the method we'll be implementing in openFrameworks, and the bottom is linear interpolation. So if I jump from the value of 0 to 200, we can see the result. This is going to happen over 2 seconds. Alright, I'm going to go ahead and make this time a bit longer. Let's go 10 seconds. And so we can get a clearer idea of what's going on here. Now you can see the top, we went from 200 to 0 nearly instantaneously over one sample. These filtered responses will go to this location, the same location, over that set amount of time. And it appears as though the low-pass filter got there before it did, but we are rounding, and this actually will not stop until this filter has reached its end. Because it's an infinite impulse response filter, mathematically it will never actually get all the way there, but we are storing digital audio and digital signals, so eventually it'll be close enough that the computer wouldn't even be able to tell a difference, let alone a human observer. Alright, so let's play a little bit and see which we'd like best as a result. So if you're a user of a program and you're moving around, I kind of like the responsiveness of this low-pass filter. The linear interpolation it just doesn't respond as quickly. One side effect is, as we see here, if we jump values, this actually moves pretty quickly to the halfway point, whereas this takes exactly half the time. So there's a give and take, and what you would want to use might differ based on the context. But for the most part, prefer the low-pass filter. And I've called this a smart low-pass filter because this coefficient is actually generated automatically based on the ramp time, and we'll show you that, or I'll show you the equation in a bit when we get to the code. So let's move this down to something we'd actually end up using, like 100 milliseconds or less probably. And we can see the responses are actually not so different between the two in lower settings, from this point of view at least. Let's jump from 0 to 200 to 0 to 200 a few times, take a look at that. And we can see most of the results are towards the target, whereas these are more evenly distributed. Let's raise the time again, 0 to 200. So this is the response we're going to get, and this is what we'll be implementing, and will work for all of your parameter smoothing if you're using a MIDI device, translating that into audio stream, and if you're using a GUI or any mouse input or any other kind of input. This is not exclusive to audio. You could use the exact same algorithm to change your graphics. So they say the location of an object from A to B and ramp that time and move that position non-linearly, and it's a bit more appealing. It's less mathematical, or less rigid. It's not less mathematical, of course. Okay, so let's go ahead and jump into openFrameworks. As I said, we'll continue from where we left off, and to test this out, we are going to just play a low frequency sine wave, because that will be the most obvious case where we'll need it. So we no longer need this. We just need a single oscillator to be heard. And we'll use the oscillator we built in one of the first tutorials. Sine Tone, we'll call it. All right, and we'll set up that sine tone. Let's do 100 hertz, fairly low. We'll start at 0 phase, amplitude. Let's do 0.7, and sampling rate is sample rate set above. All right, and we won't use the auto pan that we made in the last tutorial. So let's go ahead and get rid of that. We will need this position still. All right, and frequency. Hey, you know what? Let's just let's keep the same variables as before. Since they're there, let's use frequency and amplitude. Okay, we won't be changing the frequency yet, at least. And let's use our current sample, monophonic. This will be current sample equals sine tone dot get sample. So we just have a monophonic sine tone. We're scaling that down as I like to do so I don't get hurt. Let's scale it down less though. And we'll use our position of our mouse. If you haven't been following along, we are getting that position with the mouse X. So left is mouse on the left side of the screen, right is mouse on the right side of the screen. So we'll pan that, and let's map the amplitude to the Y position. So amplitude equals of map Y 0. Let's do height and 1 to 0. And we'll flip that upside down because the way the pixels are read on the screen again. Okay, so that won't be enough yet. We need to make sure the amplitude of the oscillator actually is applied. So before we get the sample, sine tone, remember we made a set amplitude function. And we'll set the amplitude to be amplitude. Okay, so that'll make sure our amplitude of the sine wave is actually accurate by the time it is producing a sample. All right, looking around to make sure I didn't forget anything. Again, the panner is returning a frame, which we made in the last tutorial, and we are pushing that frame out to the buffer. Make sure everything's happy. It looks to be. Alright, so the crackles and pops didn't come out so well in the last tutorial because of the compression of my screen recorder, but if you're trying this out yourself, you'll definitely be able to hear them. And we're getting them from the pan and from the amplitude. So, as I said at the end of the last tutorial, this is happening because we're changing the amplitude almost instantaneously, and that is essentially making a pop. It's moving the sample to a different location so quickly that it's audible. So we want to slow that transition down to a point where that pop will not be audible, but not so slow that it adds a lag to the program. So let's get on to that. So we're going to add a new tool to our audio tools file. And let's call this smoother. Why not? Class smoother. Let's be a little more specific. Parameter smoother. Okay. And we'll have public and private variables. as we typically do. Okay, so quick note, I did not invent this code, and I wanted to give a shout out to Alex Perez, who contributed what I believe the most important part. And I'll note that I found this code originally in RackAFX, Will Perkel's RackAFX, which is a program that's free for Windows, used to program VST instruments, also C++. I do recommend checking out RackAFX. It's free and it's pretty convenient. So we'll be implementing the same algorithm used in RackAFX for parameter smoothing, the same one as I showed in this middle test here. So to do that, let's first move a little backwards. We do know we'll need to store some variables for the function. We'll need a float, and we'll call it A, float B, and float Z. Okay, and I've kept the naming the same, so you can look at the RackAFX source code, and everything's identical. Okay, so we'll need a new, we have 2 pi. A will be our coefficient. And a coefficient is nothing more, in this case at least, than a scalar value. Let's see. Actually, first, let's not do that. I changed my mind. So first, let's make our smoothing function and explain that. So this will be, our function will return a float, and we'll call it process, and we'll process the input that we need. So float input. All right. So we have input, output. All right, so we're going to get a number, and we're going to return a smoothed version of that. All right, so this will be Z equals input times B plus Z plus A. And then we will return Z. All right. So you can see there's a bit of recursion here. This might be confusing at first, but we'll get there. So Z is equal to the input times this value, which is a scalar, plus the previous input, plus, oh, times A should be, sorry. So A is a scalar, and B is a scalar. Z is our previous input. So we're going to set Z, or this equal to Z, then return Z, but this Z is not up to date. This is our previous version of Z when this math is done. So that's a little confusing. So we're storing one previous sample here. That's why it's a one-pole filter. Okay, so we don't know what A or B is, and that's the math. This is A, what A and B is determines the cutoff frequency of our filter. It gets pretty confusing, but just think of it this way. The cutoff frequency is based on the scale of our input and the scale of the output. So if we take more of the input than the previous input, then we'll have more high frequency content. If we take less of the current and more of the old, we'll have a more low frequency or less high frequency. And that's true, and it's confusing, and it's not entirely necessary that you understand why. It took me a lot of filters looking at to understand why these things work and how, and it's still not important that you know exactly how that works, just that it does. All right, so this is the part that Alex contributed that I'm really fond of. A equals exponent of negative 2 pi divided by smoothing time in milliseconds times 0.001 to translate milliseconds. Might as well be more specific here. To translate milliseconds to seconds, and then times the sample rate. All right, so we have some variables I've used that we haven't told the function about yet, but we'll get there. Right, so what this does is creates a coefficient that will take milliseconds and give us, it'll input milliseconds and give us the coefficient needed to filter out and arrive at our destination, or near enough rather, by this timeline. So it's a pretty magical function, and I never would have come up with it myself, so that's definitely why I want to give credit to Alex. But a quick diagnosis, exponent is taking Euler's constant to this power. So that's not exponent as in any exponent. It has a predetermined base. If you want to do an exponent and determine your base yourself, you have the power function, which say we can take 2 to the 4th power. It has that kind of context. Okay, so just to clarify, we are doing a power here, but this is just a specific case of that we have access to in C++. It's used often enough that they made a function for that. Okay, so we haven't given, we haven't set this up right. So we need to give this sample rate and smoothing time in milliseconds. And it's complaining about A, but I'm not sure why, because we do have A here. I'm sure there's a good reason. Okay, so let's make our constructor, which will be parameter smoother, and then we'll need the smoothing time in milliseconds, and we'll need the sample rate. All right. And when we make this object, we'll go ahead and set A equal to all of this. Now everything is very happy. Look at that. All right. So B is just the inverse of A. So B equals 1 minus A. Make sure it's a float. And we'll set Z equal to 0.0. So that way when we start Z is 0, the previous sample will be 0, and B will be what's left. So this will always be from anywhere from 0 to 1, and B will be what's left of that. Okay, so once again, if that's confusing, don't worry too much about it, it will work. Alright, one last thing we will need is, well, we don't need it, but it's better. And this is a little confusing, more than a little confusing. We're going to make this an inline function. You can read up on C++ forums about what the inline function does. It didn't help me, and it probably won't help you either. Maybe it will. But they are used a lot in audio programming. It copies the equation so the processor has faster access to it, is what I understand. But you use it when there's a short equation that you use a lot. And this is definitely that kind of scenario. This will be called every single sample. That being said, this is a very efficient function. This is inefficient, but it only has to be called once. This will be called every sample. And it's just an addition and 2 multiplication. So it's not bad at all. Alright, so we actually don't need to put anything in the CPP file in this case. A very small function. Okay, so we could make a new parameter smoother, but first, let's do something else. Kind of like we did with the panner, we'll have a struct. I'll call it SmoothValue. So anytime we make a value and we want it to use the smoother, we'll just use the structure instead of a typical float. So we'll make a float and have the target value. So this is where we're trying to get. Float current value. This is where we currently are. And parameter smoother. And it won't know what this is. Because, oh, never mind. I was wrong about that. Alright, I was thinking we'd have to put this at the bottom, but it's looking around, it knows this class is here. Great. Okay, so now we have a really convenient way to store our variables. We don't have to do this, but in my opinion, this will make our code a lot clearer and cleaner. Okay, so a lot to digest. We're using our first filter, our first kind of heavy, not necessarily heavy CPU-wise, but our difficult, DSP object. So let's add it to our code. So instead of our pan position being a float, let's make that a SmoothValue. And this should be happy because we have included that document audio tools. It is. Okay. So instead of setting position equal to 0, we'll set position dot target value equals 0. All right, so it's saying try to get to 0, get there as fast as you can based on our smoother. And we haven't told our smoother how long to take yet, so let's do position smoother, and we'll make a new smoother for this. New smoother, or smooth value, sorry. All right, and this will take, let's do 20 milliseconds is pretty reasonable, and give it the sample rate. Everything should clear up here. Oh, one last thing. Go here, and let's make this a pointer to a parameter smoother. We won't worry about why yet. Just make sure that happens. All right, now it'll be happy with this equal sign. Not yet. All right. Why are you unhappy? Float and an int. Okay. I wouldn't think it's unhappy because it's a float. Okay. Not smooth value, that's what the problem is. So I named this the structure. I should have named it the class of the smoother that we just made. It's called parameter smoother, not smooth value. Now it should clear up. There we go. So we have a new smoother. Okay, so whenever we do add a pointer as a type, we'll have to do something instead of the dots that we usually use, and I'll show you here. Alright, so we go to our audio loop, current sample, we'll go after that. So our position dot our current value is equal to our position smoother, whatever it processes on our position's target value. All right, so let's break this down a bit. So we'll need, anytime we use the value, we'll use the current value. And once per cycle, we will update that current value. So position.smoother, so we're using the smoother here, and we're processing our target value. And whatever we processed will be our current value. All right, so we'll pan to our position.current value. Okay, so that's all good. One thing we need to do is take a guess what we need to change here. Is it current or target? When we move our mouse, it is target. So we are targeting this new location. It won't get there immediately. It'll get there whenever this function lets it get there. All right, so let's disable this so it won't bias our opinion on the results. Oh, we're unhappy. All right, so audio tools.h, line 43. What's it say? Syntax error missing, colon before asterisk, before a pointer. That doesn't seem right. So we have our well, maybe it does have to come after. Let's try again. I've not seen that error code before, so this will be a fun decode. Oh, that was in fact the problem. Okay, so like I thought, it doesn't know what a, oh, I should turn this off while I talk. It doesn't know what a parameter smoother is if I declare it before I declare the parameter smoother. How could it? This is reading the code from top to bottom. So I was confused that it turned green, but apparently it'll turn green if it's in the same document. Yeah, these are usually helpful, these color codings, but as you just saw, it made me make a mistake. So just be wary. Follow your instincts, I guess. But a parameter smoother is declared, and then we can use one. Okay. Now let's test. Right, so all those clicks are gone. We can move as fast as we want, and we get none of those nasty clicks. Okay, so let's go ahead and add the amplitude back in. So instead of amplitude, instead of float, let's use our new tool, SmoothValueAmplitude. Okay, and we'll follow the same kind of procedure. Amplitude.target is equal to 0.7. Amplitude smoother equals new parameter smoother. And we'll give this ramp time of 20 milliseconds at our current sample rate. Great. So the nice thing about this including the sample rate is if somebody later on you'll have different operating systems running your code and different users running different sampling rates, and you don't want this time to be skewed by a different sample rate. If this were 41K, it wouldn't be that much different than 48, but if somebody's running 96K or something even more absurd than that, there will be a pretty stark change. So all right, so let's move along. Let's update the current amplitude equals amplitude smoother, and this is where we use an arrow because we used an asterisk earlier, and don't put any more thought into it than that yet, just know that's why. Amplitude.target. Alright, when we set the amplitude, we want to set it to the amplitude current value. Alright, and then when we adjust the amplitude, we want to adjust the target value. Alright, so the way I did, we have an error here. Here we go. Dot current value. It might be happy with that. I have to think about this quickly. Yeah, let's go ahead and set the current value before we go doing that. So we'll run this process once before the audio thread starts. So amplitude current value equals amplitude, run the smoother. Oops. Process amplitude target value. All right. No clicks anymore. Fantastic. All right, so that's really useful and really absolutely necessary. And it's a good thing to learn early because I just left those clicks for a while and that's embarrassing. Don't do that. But that's not fun. So let's just do something a little more, fun to listen to before we end this here. So let's not mess with the amplitude with the mouse Y, but instead the pitch of the oscillator. So let's make a new SmoothValue frequency. Get rid of our old lame float. Frequency. All right, now let's do something absurd. Let's take, 5 seconds to get there. So 5,000 milliseconds. and then let's run our first process here. Alright, so now we use the frequency current value. And we'll have to set that before we use the sine wave oscillator. So Sine Tone dot set frequency dot current value, and we'll also need to update the smoother. Frequency dot all right, so everything looks happy. And let's change this to frequency target value. Instead of 1 to 0, let's do 2000 to 40. Huh. What has gone wrong here? Frequency target value is 2000 to 40. Alright, and we're setting the frequency here. Frequency current value. Oh, okay, I used the amplitude. That's the problem. Frequencies. I was using the wrong smoother here. Alright. So it's taking a little more time to get there. Really fun, just like I promised. Okay, so on the next tutorial, we will be talking about loading an audio file and playing an audio file. This is not as trivial as you might expect. See you then.